make some approximations to perform the calculations of what we're going to do. So for instance, if we're going to compute the area of a circular region, we know that we need to multiply by pi, but you know that pi isn't a number that we can put it exactly as one number. So what can we do? We usually approximate. So instead of using pi as like the irrational number, we use an approximation, for instance, 3.14 or 3.1416, etc. Of course, considering the accuracy of the estimation, we can use different significant digits for the number. So what can we say? We say that to talk about this number, pi, we don't talk about a crisp number, I'm sorry, but an interval, is the interval, in this case, is going to be the interval between 3.14 and 3.1416. Every number between these two numbers, well, every number in this interval is going to be a well approximation of the number pi. So this is a motivation to define fuzzy numbers. So, okay, we notice that every point in this interval, in the interval that I put here, has a different rate of correctness in quote. And at least one number, in this case, the exact value of pi, that is a irrational number, so we cannot write it here in our presentation. An exact number is correctly defined as pi. So this leads to our next definition that is going to be of fuzzy numbers. A fuzzy number is a fuzzy set in the universe of discourse of the real numbers R. Okay, remember that the universe of discourse is another way to talk about universal set, the universe. So it's such that at least one number satisfies that the membership function evaluated in this number that we have denoted here like M is equal to 1. And also, it satisfies another condition that is called that A is a convex fuzzy set. So here we're not going to go so deep in this definition because it is not something that we're going to use a lot in our presentation. But well, this is the definition of a fuzzy number. The idea of a fuzzy set to be convex is that the membership function goes up and then goes down and then doesn't go up again, like all those examples that Carmen gave us in the last part, like the triangle membership function, the trapezoidal, and the Gaussian function. So in this case, we are going to I'm sorry, I cannot see the chat. Well, I cannot read it. If you want to ask something, maybe Carmen could help me. Okay, so we're going to use a very special type of fuzzy numbers. It's going to be triangular fuzzy numbers, or just triangular numbers to be short. What is a triangular number? It's a fuzzy number with membership function given by this equation. Okay, where A1 is, I think it should be strictly less here. Well, okay, so maybe you don't see too much in this definition, but if I show you the graph of this membership function, you will see why it's called triangular number. It's going to be something like this. The value at AM is going to be exactly 1. The value at A1 and A2 is going to be exactly 0. So it is the line that connects A1, 0 to AM, 1 and AM, 1, 1 to A2, 0. And we characterized a fuzzy number with this array. The three numbers A1, AM, and A2 are going to define the triangular number. And a very important case occurs when AM is the middle point of the interval with extreme values given by A1 and A2. In this case, this number, this triangular number, can be written. Okay, so you see that A1 and A2, and the middle point is the average of A1 and A2. And in this case, we're going to write the fuzzy number just as the interval given by A1 and A2, provided that we already know that the AM value is going to be the average of these two values. So this is an example. In this case, this is the graph of the triangular number 1, 9. You see that the average of 1 and 9 is 1 plus 9 divided by 2 is 5. So in this case, the maximum value of the membership function is at 5. Okay. So, okay. So if we're talking about numbers, we want to make arithmetic operations with them, right? Like normal numbers. So we're going to define some operations with two triangular numbers. In this case, if we have two triangular numbers given by these two arrays, we're going to define the sum as a triangular number with the first entry of the array is going to be the sum of the two first entries of the corresponding array. So this is going to be like a component-wise operation where we have to notice that this is not a vector as we know them. You know, this is a triangular function, okay? And the multiplication by a real number r, again, is going to be the fuzzy number, the triangular number, with the first entry multiplied by r and the middle multiplied by r, okay? So a lot of good things happen with this definition, especially these operations are associative, are commutative, okay, associative, I'm sorry, and commutative. All those operations can be seen as, we can perform calculations with triangular numbers. Especially, we can take the average of triangular numbers. If we have n triangular numbers, we define its average as, as the way we define the average normally. The sum of all the numbers divided by the amount of numbers. Okay, so in this case, it's going to be divided by 9. And here, there is the plot of these three triangular numbers. Its average is given by this black thick graph. Okay, so I don't know if you can see well, if you can see in the graph how we perform this operation. Okay, so sometimes it is necessary to represent a fuzzy number using just a real number. Okay, so in this case, we have to choose a number that will represent the entire fuzzy number. In this code, it's called diffusification. There is a lot of different ways to define the diffusification of a fuzzy number. But in this case, in the case of the triangular numbers, we have a simple choice. It's going to be the number in which the value of the membership function is maximized. In this case, it's going to be at the value am. So, in this case, we're going to define the diffusification of a triangular. Sorry, it's a mistake. A1, am, a2 by the number am. Okay, so here we're going to stop with the fuzzy numbers to start with the linguistic variables. It's going to be something like a kind of, I think it's a little complicated, so if you have any doubts, if you have any questions, you can ask whenever you want. Okay, so Salle said that a linguistic variable is a variable whose values are words or sentence instead of numbers, okay? And these words of sentence are taken in a natural or an artificial language. For instance, here as an example, when we say John is young, we are less precise than when we say John is 25 years old. Okay, so he would just say he's 25. In this sense, 25 and young are two values of one linguistic variable called age. Those two terms, 25 and young, are values that the variable called age can take. And in this case, the number 25 is more precise and more informative than the other value that is young. Okay. And this is one of the main idea behind fuzzy logic to try to study things that are not as precise or as precise as numbers. Okay? So I'm going to apologize in advance for these draws. I draw this, and I hope that you will understand the idea. Okay, so to define a linguistic variable, we're going to start remembering what is a variable in the in the informatic point of view. So what do we do when we assign a variable, when we define a variable? What we do is that we assign some space, some well, I'm going to call it space, with the label of the variable. In this case is x. That's the name of the variable. And we define where the values of this variable are going to be. This is called the universe of this course. For instance, if you are talking about a programming language like C++, I don't know, you define the number of the variable and you say it is a float number, it is an integer, or you say whatever you want. This is the universe of this course. But you also have to define a restriction of the universe of this course, because not all the times, if you define, for instance, a variable, a real number, not every real number is going to be permitted, to be allowed to be here in this variable. Okay, so in this case, for instance, we're going to represent the variable as a suitcase. This is the label x, and the universe of this course is going to be every object. Okay, every object. So in this case, we have, for instance, a boat, and this is a boat. This is in the sea. Okay, you see that the waves. And this is a toy boat. Okay, a boat, a tiny boat for kids to play with. And we're going. So in this suitcase, this big boat, cannot be assigned to this suitcase, but the little boat can. So this is an assignation. In this case, if we assign an element to the variable, we have, well, an assignation. In this case, x, in the variable x is going to be this toy. Also, well, here I put the restriction of the universe of this course. Is going to be called R. And this is a subset of the universe of this course that has all the elements that can be put inside this suitcase. Okay, so in this case, I just put one element, but a lot of things can be put in a suitcase. Okay, so if we formalize this motivation, this idea, what do we have? We have that a variable is a three tuple x, u, r, where x is the name of the variable, u is the universe of this course, and r is a subset of u. And this represents the restriction of the values of u. And something important is that r depends of x. Okay, for every variable x, we have a different restriction of the universal set r. So r is a function of x, and there's here a lot of abuse of notation, because we probably will may need another definitions, but let's put it simple because this is not the main subject of this tutorial. So I trust you can understand this because we're going to put it in the next level. Okay, so, okay, and again, if we assign an element of the universe of this course to the variable, we have this equation represents the assignment of the value u to the variable x. You know that you have put the value u in the variable x, like you put the toy inside the suitcase. Okay, and again, as in a similar way that in the operations of sets, here, instead of saying that R is a subset of U, we can say that R is a function from the universe of this course to the set 0, 1. Okay, this function is the membership function. For instance, in this case, the membership function of the restriction R evaluated both is 0 because 0 is not an element of this restriction. But if we evaluate the membership function in the toy, we're going to have 1 because this is going to be part of the restriction. So with this in mind, we can generalize this idea of variable to fuzzy variables. So what is a fuzzy variable? It is also it also has three components. The name of the variable is going to be x in this case, the universe of this course, and R is going to be a fuzzy subset. Instead of a subset as the normal variable, in this case, R is going to represent a membership function from the universe of this course U to the intervals 0, 1. And this fuzzy subset represents the restriction of the values of the variable x to the values of the universe of this course U. Okay. So now we can talk about linguistic variables. Okay, so as we said before, a linguistic variable differs from a numerical variable in that its values are not numbers but words in a universe. Okay, a linguistic variable also is a concept of a higher degree than a fuzzy variable, because in order to define a linguistic variable, we're going to need the idea of fuzzy variable. So I can trust that you have understand the previous part because we're going to use it to define the linguistic variables. And also, a linguistic variable is associated with two rules: a syntactic rule to define new terms, new values of the variable, and a semantic rule that will give them some meaning in the context. Okay, so this is the definition of a linguistic variable. In this case, it has 5 elements: x, t, u, g, and m, where x is the name of the linguistic variable, t is the linguistic values of x. Okay, so every value that x can have is going to be here in t. These values are usually called terms. I didn't put it, but I think it is something good about all these ideas is that we have like parallel in real life. Okay, so in this case, the term of well, we will see what am I talking about. And each value of x in this case is going to be a fuzzy variable. So linguistic variables is made by different fuzzy variables. Of course, we have the universe of discourse. In this case, the universe of discourse is going to be the universe of discourse of every fuzzy variable in the of the linguistic values. And a syntactic rule that is usually in the form of a grammar, a grammar in the theory of computation. And at last, a semantic rule that is the meaning of the value. In this case, the meaning is defined as the membership function of the fuzzy variable. Okay, so we're going to give you an example. Okay, so here is an example. In this case, the name of the linguistic variable will be h. And the values that the age can take will be very young, middle age, old, very old, and others like not young, not very old, etc. Okay. The universe of this course is going to be the integer numbers from 0 to 100, and we have these two things. The grammar is not going to be precise in here because it's not part of the tutorial. But you know that the semantic rule is going to be the meaning of every term. Okay, every one of these values is called term. So we're going to define them. Okay, so we have to make a distinction here that if one term appears just by itself, it's going to be called an atomic term. For instance, in this case, young is an atomic term. So here we're going to define the membership functions of the atomic terms. Vy means very young, y means young, a means middle age, o means old, and vo means very old. So in this case, you can see that every term is a triangular set, a triangular number. Okay. Well, this is not a triangular number. I'm sorry. Very young and very old are not triangular numbers. These are well, its graph is a trapezoidal graph. So also, besides the atomic terms, we can define some other things. In this case, it's going to be called modifiers. For instance, we can have the modifier not, the modifier n. In this example, for instance, not young is going to mean, we're trying to say what it means term. Is going to mean, well, the meaning is going to be given by this membership function. The membership function of not young is going to be the complement of the fuzzy set young. So it's going to be 1 minus the membership function. And it's going to well, that is applied to two terms is going to be given by the intersection of these two fuzzy sets. Okay, so okay, so here we have something because we want you to put this in practice. So we have given to the organizers a link with several Excel files that we're going to use to show you what this is going to look like in real. Okay, so Karime Martin has raised her hand. I don't know how to. Okay. So you can talk now, I think. I don't know. Karime, are you there? No, I don't know how to unmute her microphone. Okay. Can someone please help me with this? Karime Martin. Okay, now Karime, you can unmute your microphone and ask. Or write the question here in the chat. Okay, while we expect questions, I send a link to these files, to these Excel files. I don't know if you can see them, if you have access to them. Okay, no. So, oh, okay. Okay, so we wait, but I'm going to give you this link again. I don't know if you can see this. I'm sorry. Okay, so over there, you're going to find several Excel files. We're going to open this one. It's called Linguistic Variables. example and exercise. Okay. I don't know. Okay, for those who can see the Excel, we have here, this column will have the universe of this course. It's going to be the integers from 0 to 100 here. And I have evaluated every membership function. In this case, very young, going to be, it has these values. For the number 0, it has the value, the degree 1. For number 10, it has the degree 1.8, and so on. Now what happened here? I think it has to be a 0. Okay, so we're going to plot these membership functions just for you to see this. Okay, so here we can see the plot of all the atomic terms of this linguistic variable. Instead very young is this trapezoidal number. Young is this triangular number, middle age is this triangular number, and so on. Okay. So So we're going to construct these new membership functions from the membership functions of the atomic terms. For instance, not young was defined as 1 minus the value of, of young. Okay. So in this case, not young of, okay, so here we have something that may be not real according to real life, but this is just an example. Okay, because some child, a newborn child, according to our definition, is not going to be young, but okay, you understand the idea. So this is the membership function of the term not young. And if we plot these functions, Okay. Oh, I'm sorry. I made a mistake. It's not this variable. It's this one. Mhm. I don't know what I did. Okay, again. Okay, so here they are. The blue graph is the graph of the membership function of the value young, and not young is the complement. Okay. So we can visualize the membership functions, and also, just in this case, if we want to define the membership function of the term young and old, what we're going to have is minimum of these two, no, of this one. Okay, so in this case, I want to plot this. You to see. Okay, I made a mistake. I need to put this. Okay, so in this case, we have these two graphs of young and old. And as you can see, the minimum of the fuzzy sets is always 0. So the intersection of these two fuzzy variables is 0. This is the 0 function over here. Okay. I don't know if you have something to say, something to add to my example. Because we want you to make an exercise. No, no questions. So, okay, this is the example. So we're going to ask you, because you don't want to ask us, we're going to ask you to do this exercise. Okay, here we are going to consider the next linguistic variable. This variable models the credit score level of something. In this case, the name of the linguistic variable is credit score, and the only atomic term is high. The universe of this course is the even numbers, even integers to 0 to 10, from 0 to 10. Okay, the membership function is given by. Okay, I hope you remember this notation. In this case, this means that for the value 2 of the universe of this course, we have the degree 0.2. For the value 4, we have the degree of membership 0.4, and so on. So in this case, 1 is exactly the 10 is exactly 1 because that's what we expect, right? High credit score is 10. Okay, so okay, and another thing is that with this notation, when something is 0, is the degree of membership 0. We're not going to put it in our equation. Okay, so here the value 0 of the universal discourse as membership function has degree 0. And also we have these modifiers, the modifier not, very, and fairly. So for instance, the membership function of the term not high is going to be the complement of the membership function of high, that is 1 minus the membership function of mu high. A vary is going to be the membership function the square. Okay, and fairly is going to be the square root of the membership function high. Okay, so with this in mind, I'm just going to show you the Excel. Okay, I don't know what I did here, so I'm going to close this. And here in this part, we can see the exercise. So it is very simple. We just want you to practice a little bit because we're going to make some examples that will need all this information. So we want you to be prepared for the examples, for the applications to business. So here is, and this is what we are going to ask you to do, is to write the degrees of the membership of every element in the universe U. Okay, so it is the numbers. The even number is 0, 2, 4, 6, 8, 10. And then draw the graph of the membership function. In this case, this is just the membership function of the value high. And then determine the membership function of the composed terms not high, very high, and fairly high, and plot them. Okay. So I don't know. Do you have any questions?
And we would like to see your graphics for the assistant.
Yeah, we would like to see if you are understanding what we're saying, because we're going to use all this stuff in the next part. And also because this is a tutorial. So. Okay, so we will be here for any question. We're going to give you some time if you want to practice this. Okay, so again, what we want you to do is to download the file Linguistic Variables example exercises that is in the link that we have put it here in the chat, and then do this. Okay, so I'm going to put again the membership function of high definition. I'm sorry. Oh. Something important is that all these calculations can be made in a lot of programs or uh, programming languages. Here we have chosen Excel because it is the most common tool for all of us. So you can do it in, MATLAB or
Any questions, or you can write your question in the chat.
So maybe 5 minutes for you to finish this exercise. And if someone wants to show us what they have done, I know it is not too complicated, but at least that you have understand all the notation and terminology so far. But if you want to comment something about this, if you knew all these topics and how you have applied it. Okay, so far so good. Does someone want to show us the graph? Okay. Well, I'm going to show you how we have done this. This is very simple to memorize because the degree of membership of every value of u is just the number divided by 10. So in this case, the membership of 0 is 0, The membership of 2 is 0.2. The membership of 4 is 0.4, 0.6, 0.8, and 1. So, if you see, I would like to ask if someone, okay, so you've already seen it, but this is the graph. Okay, I'm sorry, I don't want this to be like this. Okay. So this is the membership function of the high value of the credit score linguistic variable. So if we're going to define the membership function of the term not high, is just 1 minus this one. And the membership function of very high is going to be this value, the square of this value, and the of fairly high, the root square of this value. Okay, so if we plot these membership functions, okay, I'm sorry. Okay, I hope you can see the idea here. So oh, I'm sorry, I made a mistake again. I don't know what. Okay, I'm sorry. Okay, this is the. So you see that not high is the complement, right? Is 1 minus the membership function of high that I don't know why it is not plotted here. Okay, very high is the parabola given by the square of the value. Okay, so in this case, the closer to 1 is going to be higher, but not so high, because very high means that for instance 0.4 is not so high, but it's fairly high. Okay, so that's why the degree of membership of 0.4 is quite bigger than the membership value of very high. Okay, this is an example of how to construct new values of a linguistic variable from the membership functions of the atomic terms. Okay, so back to the presentation. If you don't have any questions, we're going to take another break of 10 minutes, and we will see us back here at 11 o'clock. clock, okay?
Okay. Can you see in ResearchGate, you can find our papers, Foxy Logic that apply to evaluation. Here is application to international trade. We can see our papers. And here, this is Foxy set theory applied to accounting science. You can see, okay, it's not free, but you can find information about this work. Here an example, an example of Foxy logic applied to personal selection in complex organizations. This is a case of Mexican football team. Okay, this is interesting, and there are some papers about Foxy logic to apply in social science. Okay, thanks. In a 1 minute, we continue. Okay, we continue. Remark. And this is an important remark of about FAXI sets and what is the difference between FAXI set or FAXI logic and probability. The notion of FAXI set is something incorrectly considered as a type of probability. Although there are similarities and links between FAXI sets and probability, there are also substantial differences. A good example that demonstrated the conceptual differences between statistical and FAXI classification is the one given by Bestek. In the example, a person who is dying of thirst in the desert is given 2 bottles of fluid. One bottle labels that it has a DOI-9 membership in the class of fluids known as non-poisonous drinking water. The other bottle's label states that it has a 90% probability of being pure drinking water and a 10% probability of being poison. Which bottle would you choose? Here we have 2 bottles, FAXI bottle and probabilistic bottle. The both labels are .9, but the difference is here. This is a FAXI bottle, and this is a probabilistic bottle. This is quite a possible science. There was 1 to 10 chance of it being poisonous, and the FAXI bottle contains swamp water. Recall this number is the value of membership function. This is a probabilistic number between 0 and 1. Then both bottles have a number between 0 and 1, but this is probabilistic, and this is a membership value. This also makes sense since Schwann-Water will have a probability involves crisp set theory and does not allow for an element to be a partial member in a class. Probability is an indicator of the frequency or likelihood that an element in a class. So theory deals with the similarity of an element to a class. Then I prefer the Foxy model. Okay, this is important, the difference between Foxy logic and probability theory. Okay, now we're going to talk about decision-making theory. This is an important topic for this tutorial because all about of theory of applications of Foxy logic to business implies a decision making. For this, we present a video by PhD or Dr. Martin Flegel from La Salle University in Mexico. And 1 minute, please. I find the video. Okay, it's here.
Good morning.
Can you hear
this
the
is
video?
a brief introduction to the decision-making theory.
Okay, thank you.
First, we need to start with what is the decision-making theory. Simply, the decision theory is a theory about decision. Of course, because we are talking about decision-making. But what is a decision? Decision can have many definitions from many authors, and there is no only one common definition. But mainly, a decision is a choice, selection, election made between alternative courses of action. We can talk also about options or alternatives in a situation of uncertainty. The last part of this definition is very important because usually we do not make decisions under certainty. Usually, most of our decision making is under uncertainty because we are not 100% sure what will be the result of our decision. We can guess, we can calculate some probabilities, but we are not 100% sure what will happen. Almost everything what we do includes decisions as we analyze more alternatives or options. I can ask you a very simple question. When was the last time when you made a decision? If you think about this one or talk with your colleagues, you are thinking about some decision you could have made in the morning, but actually the last time when you made a decision was right now. You are thinking whether to answer my question or not to answer my question. This is also a simple decision. So your last decision was more or less a few seconds ago. Decision analysis provides a structure and guidance for thinking systematically about decisions. We do or make decisions all the time, many decisions during the day, but sometimes we might get a kind of a lost or with troubles to understand our decision making. So if we apply the decision making theory, it will give us and introduce some step what we need to do step by step until we solve a decision making problem. The decision process is then described as a series of steps. Usually we start with the initial information output, then we make some analysis, and then it culminates in a resolution, namely a selection from several available alternatives. Moreover, decision analysis provides analytical tools that can make the required thinking easier. I already said that we do or make a lot of decisions all the day long. So another question can be, are all the decisions the same? What do you think? Are we doing the same decisions every day, every day, every day? The decision can be or look the same, but usually, even though we have the same two alternatives, we have the same problem, and we might have the same criteria, the decision might not be the same all the time, because the circumstances, the decision environment that is all around our decision problem may be different all the time. Is making decisions difficult? It depends. Decision can be easy, depending if we are deciding about very easy, simple decision-making problem. For example, whether to eat pizza or pasta. This is very simple decision, but many decisions may or are very difficult because they are very complex. Okay. So why are decision or why can be decision-making difficult? First, decision can be hard because of its complexity. The decision problems can include many alternatives, many criteria, a lot of information, and again, there is an uncertainty inside the decision making. However, the decision analysis provides effective methods for organizing a complex problem into a structure that can be analyzed. So when we see a decision-making problem, whether simple or complex, we need to define its structure, the problem, the alternatives, the outcomes, the consequences, and when we think kind of creatively and systematically about this decision problem, we can minimize its complexity. Second, the decision can be difficult, again, because the uncertainty in this situation. In some decisions, the uncertainty is the main issues. Okay, mainly in the complex decision-making problems, there is a huge amount of uncertainty. Again, decision analysis approach can help us to identify the important sources of uncertainty and representing that uncertainty in a systematic and useful way. We cannot, in most of the cases, eliminate the uncertainty from the decision-making problem, but we can minimize the uncertainty, or we can restructure the uncertainty into a simpler way, simpler structure. Again, applying the decision-making theory. More decision maker may be interested in working towards multiple objectives, but progress in one direction may affect the progress in others. And again, this causes some difficulties in decision-making process. First, we may want to maximize our output, but on the other hand, we can also minimize the costs. And those are two different ways or two different objectives that can be kind of in a clash. They can be kind of against each other. And then the decision making can be kind of difficult. Usually, we must make decisions between expected return and the riskiness of the decision making. And last but not least, decision may be difficult because the different perspectives lead to different conclusions. For example, I usually ask, what is the main problem of Mexico? You may say that there are no problems in Mexico, but if you think about it a bit deeper, someone can say it's a corruption. Someone may say it's the violence. Someone may say it's an education, etc., etc., etc. And when we have these different perspectives, it may be difficult to define which one to select and which one to solve. And again, for example, if we select corruption in Mexico, we are going back to the first point. It's again a complex problem, because corruption, how to solve corruption? There are many attributes, many criteria, many information, much information, many alternatives. So it's complex, and solving one part of this problem of corruption, again, there is a lot of uncertainty inside. So all those 4 points of several ideas or examples of difficulties can make the decision making even more difficult. Okay. Different individuals may look at the problem from different perspectives. Why? Because they have different background, different level of education, they are studying different study program, different careers, they have different skills, knowledge, experience, so this can cause a problem. On the other hand, different perspectives in decision making, it is also something valuable because it can generate more ideas, more alternatives, more solutions. So from the point of view of the creativity in decision making, the different perspectives of the individuals, it is a good point. Again, the different individuals, they may disagree on the uncertainty or value of the various outcomes. The obvious reason for studying decision analysis is that carefully applied decision techniques can lead to better, or if you want to say, good decision. Okay. Of course, we don't want to make bad decisions because no one wants to get some bad outcome from the decision making. But what is a good decision? There is no a simple answer for this for such question. Usually we say that the good decision is a decision that gives us the best outcome. Okay, it gives us the most biggest profit, most money. Okay, or minimize the cost, or any other outcomes you may think. However, sometimes we can construct a really huge, complex decision-making problem, including the most of the information and our experience. But sometimes there can be a lucky outcome due to some unpredictable circumstances. Again, there is the uncertainty. So sometimes we do bad decisions, but we can get a better outcome from a good decisions, very well structured decision-making problems. Okay, such as a global crisis can be the unpredictable outcome or circumstance. Right now, the coronavirus situation it was also unpredictable, and right now it's affecting all our decision making. Okay, so we make a good decisions, but still we can have some unlucky outcomes. Simpler, from my point of view and from my experience, the good decision, it's a decision that makes you happy. And if this decision makes you happy, then of course it was a good decision. Although decision analysis cannot improve your luck, it can help the understanding of the analyzed problem. This understanding must include a structure of the problem as well as the uncertainty and trade-offs of a particular alternatives and outcomes. Important, although decision analysis provides a structure and guidance for systematic thinking in difficult situations because the uncertainty, it, however, does not claim to recommend an alternative that must be blindly accepted. Why? Because we should rather understand the decision analysis as an information source providing insight into the problem situation, uncertainty, and objectives. Decision analysis also does not tend to replace decision maker's intuition or be a competitor. Rather, decision analysis tends to be a complement and work alongside with a decision maker. And we can also understand it that the decision analysis justifies whether previous actions were appropriate or not. Remember, we need to present the results of our decision-making process as with this information, these alternatives, these criteria, and this evaluation or this method we use in the analysis, this is the best result. However, if we change anything in our decision-making model, we include or replace some alternatives, more criteria, different criteria, or we update the information, we download new data next year, the results can or may be different. That is why the decision-making process is a support for our decision-making. Remember that the one who makes the decision, it's us, Okay, the decision maker is making the decision, so we are the last one who should or who must make the decision. And for the last part, it's also an important to understand that all decision-making process or any decision includes the subjective judgment. What is a subjective judgment? It's the level of experience, knowledge of any decision maker who makes the decision. The decision analysis allows the inclusion of subjective judgments, or better, decision analysis requires personal judgments. Decision making requires us to provide the initial information, to select our alternatives, to select the criteria, to know from where to download the information. Okay, but we must keep in mind that anyone's insight about the uncertainty and preferences and alternatives and the information can be both limited and misleading. Okay, we must be aware that our points of view, our perspectives can influence the whole decision-making process, our selection of alternatives. If we want to minimize the effect of subjective judgment, we should include more decision makers, more opinions inside the decision-making process. Ideally, minimum at least 3 decision makers, because one may be biased to one side, to the left side, one might be biased to the right side, the other might be somewhere in between the left and right, so we can kind of make the average from the 3 decision makers' points of view, and we can limit it or minimize the subjective judgment. The more decision makers we have involved in the decision maker, the better. However, there is no best number of how many decision makers we should involve in the decision making process.
Okay, thank you. We have a questions in the chat. 1 minute, please. Okay, thank you, Jesús. The question is, if they are not probability, what can we say about the maximum and minimum of the function that we graph? Okay, the Foxy set and the probability about are related. For example, the probability function, the Gaussian function can be a member function. But when the probability is deterministic and the Foxy logic is Foxy. One is a membership and the other may or may not occur. The difference is the membership function. Okay. I'm sorry, again, and we have a presentation. I'm sorry, it's very far. Okay, this is a difference between the classical set. The probabilistic is defined in the sense of classical set theory. As you can see, the boundary is clear. It is easy to see. It is easy to see if an element belongs or not of this set, but on the Foxy set, the boundary is Foxy. It's not clear if an element belonged or not of this set. This is the difference. This is the difference between 2 concepts. The probability is based on classical set theory, and the Foxy set is related with the membership function. I'm sorry, okay. This is the most important concept, and Foxy set theory, the membership function. There is a different theory for probability for probability and the Foxy set theory. Okay. Jesús, talk. Okay. Yes, can you hear me? I'm sorry. Okay, one moment. Thank you, okay. Thank you, Jesús. Thank you, Dr. Martin Flegel, for your presentation for this tutorial. And now we continue with decision making. The main objective of this topic is to consider two methods for decision making based on Foxy set and Foxy logic. First, we introduced is the Salle approach, according to which decision making is defined as intersection of goals and constraints described by Foxy sets. The second approach for making decisions combines goals and constraints using Foxy sets and diffusification. And besides, applications are made to various real-life situations requiring selecting or evaluation type decisions. Okay, we continue with Enrique. Thank you, Enrique.
Yes, I'm going to show the... Okay, so first I want to add something to the answer of Carmen of this question. Also, we can see a difference from the examples we made. Okay, I'm sorry. For instance, in this case, if we say something is old, it has, for instance, a 0.9 membership degree to the variable old, it means that is something that we can, I don't know, associate with someone old. But it is not the probability of someone to be old. It is its degree of membership. Someone that is, I don't know, 60 years old, we can say that he has, I don't know, 0.8 a membership of this variable, but it doesn't mean that it has 80% of probability of being old. So there is a distinction here of these two concepts. Probabilistic. I don't know if this clarifies something, but I think we could see this in the examples. Okay, so we're going to continue with this part. Is now related to decision making. Okay, so here we're going to reduce all the decision making to one problem. We're going to call a selection problem. It's just one way to see a problem, the problem of select something from different choices. So what we have? We have, we assume they have n alternatives or n options, A1, A2, to AN, and we want to select one of them that will be the best choice. So how can we do that? We can do that by evaluating the position to fill, okay, what we want to select, using different criteria. In this case, M criteria is going to be denoted by C1, C2, and Cm. Okay, so the evaluations are making by K decision makers. They, of course, are experts in the field. So we have also the set of decision makers. We're going to denote as E1 to EK. So until this part, we have a selection problem, but we can also add some weights of importance in the decision, because the criteria may have or may have not different weights in the decision we want to make. So the criteria can also be evaluated by the decision makers, and we can also calculate different weights for the criterion. So we have these sets of weights. Okay, this is the selection problem, our selection problem. And the idea behind the different methods that we're going to explore here that solve this problem is that after the decision makers have done their evaluations, we combine these evaluations with the techniques that we have been developed in this material of fuzzy set theory. And with this, we're going to supply an option, a best option according to our method and the evaluations of the decision maker. Okay, so in this case, because we're talking about fuzzy sets, we're going to assume that every criterion, Ci, and its respective weight, Wy, are both linguistic variables. Okay, so, and even more, to make this more precise, we're going to set the universe of discourse as the set of real numbers. And the restriction function, the membership function of each value of the linguistic variables will be associated to a triangular number. So this is going to be something quite more simple than the general case, but it will suffice to be a good examples of these methods. Okay, so we have two arrays. This is going to be the arrays. I'm sorry. Okay, we have these two arrays. One is for the evaluations of the weights, and the other one is the evaluations of the alternatives, so the choices we can make to fulfill the position. Okay, I don't know if this needs more presentation, but I think it's clear. In this case, for every decision maker, this someone that evaluates the weight is going to be a label here that will determine the value of the linguistic variable. Also here, for each criterion and each decision maker, we have a label. Okay, so here every Wij and Aijk are triangular numbers. And the problems turns out to be how to select the best choice according to these evaluations and with the machinery we have constructed so far about fuzzy logic. Okay, so we're going to begin. We're just going to give two different methods of how to do the selection. And the first one is going to be the decision making by intersections. Okay, so what do we have here? If we have a collection of fuzzy sets in the form of goals and constraints. Okay, so here we're not talking about conditions, we're talking about goals and constraints, but in some senses, it can be indistinct how you define them. Okay, because you can say that a condition of someone is to be something, but you can say also that this is the goal of your of I don't know the best choice, or as a constraint you apply to your choices, to your alternatives. So if we have these fuzzy sets, we define the decision as the intersection of these fuzzy sets. And this makes sense because if we intersect all the fuzzy sets, we're going to have a membership function that somehow describe how much this alternative fulfills every aspect, every goal, or every constraint, or every criterion, or every condition. Okay, so the intersection of these fuzzy sets is going to be called the decision. Okay, so now since we're going to give this information to the decision maker, okay, as Dr. Frey told us, this is just a tool, but we also can use the knowledge of an expert, of the experience of other people. But we want to give them something that is easy to understand. So we need to give back a crisp number. So a diffusification of the decision is required. Okay, then according to this number, a decision can be made, or a decision in the sense of what choice are we going to select. So this diagram summarizes this idea very, very poorly. I know, but we didn't want to add a lot of information at this time of the presentation of this tutorial. Okay, so we have fuzzy sets. In this case, we're going to label goals and constraints by G and C. It's something that it can be changed, of course. And then we have the decision set. It's going to be the intersection of these two fuzzy sets. Of course, the decision set is a fuzzy set because it is the intersection of the two fuzzy sets. And then we're going to apply a diffusification. Is that will give you some idea of what is the decision to be made, to make. Okay, so we're going to apply this to a concrete example. Okay, so here is. Of course, most of companies plan to produce at the lowest cost and offer products of the highest quality. So imagine that we have a company and that the acquisition of raw material, for the acquisition of raw material, the company has a 5 suppliers, okay? And these suppliers are going to be defined as these 5 letters, A1, A2, A3, A4, A5, will correspond the suppliers. And they have to fulfill 3 conditions that will be evaluated for this process. In this case, it will be the cost of raw material, the quality, and the delivery time. So in this case, you can say that some of these can be seen as goals of a good raw material. Some things can be seen as constraints. Okay, so in this case, we're going to evaluate every of these. Okay, remember that also the criterion is a linguistic variable. So every linguistic variable is going to have these values. In this case, it's going to have 5 values. The first one is going to be very good. It's going to be the fuzzy triangle number, from 66.4 to 100. Good, all that. Okay. So the expert, the decision maker, can label all these conditions to every one of the potential suppliers. Okay, so notice here that, okay, we cannot see that here, but these numbers are triangle numbers, but they are also numbers. This is the middle point, I think. So we are going to denote this just as the interval from 66.4 to 100. Okay, so we're just going to be the interval to denote these triangle numbers. Okay, so this is the evaluations that one expert made to these 5 possible suppliers. In this case, for the agent A1, the cost is labeled as regular. The quality is labeled as regular, and delivery time is very bad, and so on. Okay. In this case, we're going to choose the best choice from this one. Okay. So it will be something like, I don't know. He's going to summarize all these decisions just as a crisp number, just as a number. So the decision can be made more, is simplified. So what are we going to do? We're going to translate this label. There is the name of the fuzzy variable by the membership function. You see that now we just write the interval. It is not the 3. I'm sorry. The 3 and 3 array. It's just the interval. And okay, so we're going to apply the intersection method. In this case, we can translate that as that the relation between cost of raw material, quality, and delivery time is provided by the intersection of the fuzzy subsets that we have defined by the evaluation of each criterion. Okay, so we're going to make the intersection of these 3 sets, and here we're going to skip some steps, because of course the intersection of fuzzy sets is not the intersection of sets, is the minimum or the membership functions. And in this case, the intersection is not exactly a triangular number, but we can apply something that is called a normalized or something like that, in which the maximum value of the intersection is now 1 again. So the intersection of two triangular numbers is again a triangular number. And in the particular case, when the triangular numbers are, the middle term is the maximum value is at the middle of the interval, then again the intersection is also of the same form. So we're going to use all that information to just apply this, but I think that this is clear. So if you have any questions, you can ask. So skipping that part, we're going to have that the intersection of the evaluations in the case of the first agent is this triangular number, and this one for the triangular number, I'm sorry, and so on. So the value that we have chosen to, oh, I made a mistake here, because it should be the maximum. Okay, I'm sorry. Forget about this and think about it as a diffusification of this triangular number. Okay, so we're going to choose the diffusification, that is the value of the maximum, the maximum that we can have in this interval. In this case, is the middle point between 0 and 33.2. And in this case is the middle point of this one. So we can see, in this case, it's not difficult to see that the best choices are equally A2 and A5. Okay, because they have the highest middle term. So we can give this to the decision maker for them to decide which one is going to be the best supplier of raw material. So in this case, we can see an example of how to apply this method of intersection to select the best choice of for a supplier of raw material. Okay, so if you have any questions so far, this is the first example, and I think it's easy. Okay, so besides that part that we have just like skip from taking the intersection of these sets, and this mistake that I made of taking this is the minimum. Okay, so I think it is clear, but if you have any questions, you can ask. Okay, so for the next example, that is going to be a lot more complicated, we're going to need the next definition. It's called the Hamming distance. The Hamming distance, it is not defined only for fuzzy sets. Actually, the original term is in the informatic area, and is used to measure the distance between two strings of the same size, of the same length, and they tell you how different they are from each one to the other. Okay, so for instance, if I have the string 1, 0, and the other one is 1, 1, the Hamming distance between those strings is 1, okay, because they are different than the one in 0, 1. Okay, so we can take this to the language of sets, and if we have a subset, two subsets of the same cardinality, we can define the Hamming distance as the difference of the membership function. Okay, well, in general, it will be 1/2 because it can be, yes, it can be something like 1/2 and divided by n in order to make this in the interval 0, 1. So in this case, if we make this analogy with set theory, the Hamming distance is going to be related to the cardinality of the symmetric difference set of two sets. Okay, so it will measure how different two sets are from each other. Okay, so this can be translated to fuzzy sets also. In this case, if we have two fuzzy sets, A and B, with membership functions given by, okay, the first definition is going to be for every functions, but in this case, we're going to restrict the explanation to a triangular number given by this interval ax1, ax2, ax1, ax2. Okay, so in this case, the Hamming distance, if we make the operations, can be translated to this difference. It's going to be 1/2n, and the sum of these two sums of the absolute of the difference of the triangular numbers, of the extremes of the triangular numbers. Okay, so this is going to tell us how a measure between fuzzy sets, and we're going to apply this to our next example. It is going to be a lot more complicated. So we're going to stop here, and we're going to take a bigger break because I know it has been 3 hours now. So if you want to ask something, you're free to ask. So we see us at 12:05 to continue with the presentation. Okay, but any questions so far? Okay, thank you, Miguel. Carmen also wrote in the chat that you can ask here in Spanish, and we can translate it to English for everyone. If you don't want to ask something because you don't want to speak in English, you can write here in Spanish. Okay. So okay, so we see us in 15 minutes. Okay, just for your knowledge, the last part is going to be an example and an exercise. It's going to be quite longer than the previous one. So if you please try to be prepared to participate and to comment something or to ask whatever you want.